Hey everyone, welcome to the first video in the video series on trig substitution for Math 1452 at Texas Tech University, which is Calculus 2. So in this video, we're going to be talking about a special way to use substitution that will allow us to manipulate integrals that look similar to some integrals that we've seen before. So in Calculus 2, it's important that we remember all of the antiderivative rules we learned in Calculus 1. So specifically, the three we're going to look at in this video series are the antiderivative rules for the inverse trig functions. So each of these integrals look similar, but I want to specifically point out some key differences between them. So these three, because they are all positive, these are going to be the antiderivatives for inverse sine, tangent, and secant. And that's because they're all positive. So one thing that we learned in Calculus 1 is that anytime we have a trig function with a like cosine, cotangent, or cosecant, we're going to have negatives in those derivatives and integrals. So in particular, since these are all positive, they are only going to come from the trig functions without a which are sine, tangent, and secant. So one thing I want to point out is that the tangent, the first letter is a t, which looks like a plus sign. So we can remember that this integral, where we have a plus sign in our denominator, is going to be the inverse tangent. And that's because the t of tangent has that plus sign. So the other two integrals have a square root and subtraction. And a square root and subtraction both start with s, as do secant and sine. So that's how we can remember that those go there. However, this first one is a little bit more familiar because there's no absolute value. So that first one is going to be inverse sine. And then that last one has the absolute value, which is a little bit less familiar. So we can remember that, well, the less familiar of those three trig functions is secant. So this is one way we can use to kind of remember these in antiderivative rules if it's something you've struggled to remember moving from Calculus 1 to Calculus 2. So one thing that all three of these integrals have in common is that denominator term having a 1 and an x squared, and they're being combined in a certain way. So what we're going to do is we're actually going to see integrals that look similar to this, and they are going to have denominators that look similar to these three square roots. So the first one is the square root of 1 minus x squared, which is that same denominator for the inverse sine. The next one is the square root of 1 plus x squared, where that 1 plus x squared looks similar to inverse tangent. And our last one is going to be the square root of x squared minus 1, which is the square root of the inverse secant. So anytime we see an integral that has one of these square roots, we can immediately in our head associate, okay, this first square root has something to do with sine, the second one has something to do with tangent, and this third one has something to do with secant, because we remember the antiderivative rules from Calculus 1. So these that we have, the x squared added or subtracted from 1 that's inside the square root, are actually not going to be the integrals, the terms that we see. What we're actually going to see is that this 1 is going to change into some other square value. So for example, it's going to change into 1, 4, 9, 16, 25, something that's a square that we can recognize as a square. So I would just kind of get in the habit of remembering anytime you see a 1, 4, 9, 16, 25, 36, just whenever you see those numbers, think, oh, that's a square, and I can rewrite it as a square. Because the terms that we're actually going to see are going to look like something like a squared minus x squared. That's going to correspond with sine. Something like a squared plus x squared. That corresponds with tangent, and then something like x squared minus a squared that corresponds with secant. So all we did is we're going to change 1 to be some other square. So like I said, that's going to be 4, 9, 16, 25, 36, something like that. So whenever we see an integral that has this term in the integrand, we're going to use a different strategy to solve this, and it's going to be called trig substitution. So like it sounds, it's going to be a substitution, but we're specifically going to make use of the Pythagorean identities. So when you hear Pythagorean identities, when you hear that, that should be something that you know. So if it's not, that's an indicator to you to go back and look up what the Pythagorean identities are and make sure that you have them memorized. So all that is the identity sine squared plus cosine squared equals 1. And the other Pythagorean identity we're going to use is the analogous identity that involves secant and tangent, and that's going to be that tangent squared plus 1 equals secant squared. So there's a third Pythagorean identity that involves cotangent and cosecant, but again, we're not going to deal with any of those trig functions with a co in this video because we're only going to deal with these positive things. So we're going to use these two identities to help us figure out what trig substitution is and how to use it. So as it sounds, trig substitution is going to be a substitution. However, we're going to use theta instead of u for this substitution because we're going to have to do something with angles. So whenever you hear that or see that Greek letter theta, that tells you we're going to have to do something with angles. In particular, we're going to have to use something with SOHCAHTOA, which comes from geometry. So let's walk through each of these three square roots, how we would use our substitution here. So that first square root that has the square root of a squared minus x squared, the substitution that we're going to use is x equals a sine theta. And then we can rewrite our square root from there. So that's going to turn into the square root of a squared minus a squared sine squared theta, where we just replace that x with x squared, that x squared with the square of x. And then what we can see is we want to simplify this square root. And so what we do is we see that inside our square root, those two terms have an a squared in common. So that's going to become the square root of a squared, 1 minus sine squared. And then we're going to go back up to remember these Pythagorean identities. So if we have this equation, sine squared plus cosine squared is 1, subtracting 1 from both sides tells us that 1 minus sine squared is equal to cosine squared. So we have the square root of a squared times cosine squared. And now we can apply the square root. And this is just going to equal a cosine of theta. So what this substitution allows us to do is to rewrite our term inside our square root to be a perfect square so that we can actually take that square root and get it out of our integrand by rewriting things in terms of trig functions. So that's how that first substitution is going to work. Now let's look at our second substitution. So we have the square root of a squared plus x squared. And because we know that that's associated with tangent, our substitution just changes where x equals a tangent theta. So we can rewrite this in an incredibly similar way as the square root of a squared plus a squared tangent squared theta, which is equal to the square root of a squared 1 plus tangent squared theta. So again, we just factor out that a squared. Next, we go back up and remember that 1 plus tangent squared is secant squared. So this is equal to the square root of a squared secant squared. And then because those are both square, now we can just say that this is a secant theta. And lastly, whenever we have that square root of x squared minus a squared, we know that that's associated with secant because we remember our antiderivative rules from calculus 1, and we just rewrite this again in the same manner. So we are going to have a squared secant squared minus a squared, we factor out that a squared that's in common. And we look back at our Pythagorean identity, and if we subtract 1 from both sides, then that means that secant squared minus 1 is equal to tangent squared. And now, because everything inside our square root is a square, we can take the square root and get a tangent theta. So we can see that each of these rewrite and let us rewrite our square root without the square root. So what we need to do now is we are going to, like our normal U substitution, we need a process to put it all back together. So that means we're going to need to solve for theta. So to do that, we're going to use a reference triangle and use SOHCAHTOA from geometry. So remember that SOHCAHTOA, all that tells us is that sine of theta equals the opposite over the hypotenuse. So SOH is sine equals O over H. The CAH in SOHCAHTOA tells us that cosine of theta equals adjacent over hypotenuse. And lastly, the TOA part tells us that tangent equals opposite over adjacent. So that's what SOHCAHTOA tells us. However, we're going to need to modify this slightly because what we actually need is we need to figure out for cosine, secant, and tangent. So cosine and tangent are part of SOHCAHTOA, but we need to modify this sign to figure out what secant is. So secant is actually equal to 1 over cosine of theta. So that means that instead of adjacent over hypotenuse, it is hypotenuse over adjacent. So we are able to solve for cosine, secant, and tangent using SOHCAHTOA. So if we end up needing any of the other trig functions, we can do something similar where we know that cotangent is 1 over tangent and cosecant is 1 over sine. So we can do this exact same process, just using the same method. So this is going to be our setup for the 3 different ways that we can use this trig substitution. So that's going to be where we end this video, but in the follow-up videos, we'll work through examples using this.